Hello and welcome. Today, we're doing something a little different. We are going to become engineers, and we're going to reverse engineer what is, without a doubt, nature's ultimate flying machine. We're talking about birds and how they are perfectly built to conquer the skies.
I mean, have you ever really stopped to think about it? You see a tiny little sparrow darting around, and then you see a huge condor just floating on the wind, and they both make it look so easy. How do they do that? What kind of incredible technology is packed into their bodies that lets them defy gravity?
So that's our mission today. We're going to pop the hood, so to speak. We're going to treat a bird just like a piece of high-performance technology, and we're going to take it apart piece by piece to see exactly how it works, from its frame to its engine to its onboard computer. Okay, section 1. First things first, right? If you want to build anything that flies, you have to solve the biggest problem of all: weight. You need a frame, a chassis that is super strong, but at the same time, impossibly lightweight. And this is where it gets really mind-blowing. Just look at this comparison. Our skeletons, a human skeleton, makes up about 14% of our total body weight. But a bird skeleton, it's only 5%. That is a massive difference. Proportionally, their frame is nearly 3 times lighter than ours. That's some serious weight saving. So how on earth do they pull that off? Well, it's just a masterclass in brilliant design. For starters, their bones are hollow. But wait, that doesn't mean they're weak. They're actually reinforced with these tiny little cross braces inside, kind of like the steel girders you'd see in a bridge. Plus, they fuse certain bones together for incredible strength, and they traded heavy jaws and teeth for a super lightweight bill. Every single piece is optimized for lightness. And then there's this thing, the wishbone, or as scientists call it, the furcula. This is a totally unique piece of bird engineering. They're the only vertebrates that have one. It's basically their 2 collarbones fused together into one flexible, springy strut, and its job is to brace the entire skeleton against the huge forces of their flapping wings. It's just a simple, elegant, perfect solution. All right, so we've got our ultralight frame. That's a great start. But a light frame isn't going to go anywhere without a monster of an engine, a really efficient fuel system, and some way to keep the whole thing from overheating. And that engine? It's their pectoral muscles, their chest muscles. And what an engine it is. Get this. In some birds, these flight muscles can make up a full third, 33%, of their entire body weight. That's where all the raw power for that critical downstroke comes from, the motion that generates all the lift and gets them off the ground. You want a fun fact that shows you just how massive these muscles are? A veterinarian can't just put a stethoscope on a bird's chest to listen to its heart. The muscle is just too thick and dense. They actually have to listen from the bird's back. Now that is a powerful chest. Now, an engine that powerful needs a ton of oxygen, right? Especially when you're flying way up high. Well, birds have an absolutely revolutionary breathing system. See, when we breathe, fresh air and old air mix in our lungs. Not very efficient. Birds have a system of air sacs that creates a one-way flow of air, so their lungs are always getting a constant supply of fresh, oxygen-rich air. It's like they have a built-in supercharger. It's incredible. And of course, that engine needs fuel. Birds eat a lot of high-energy food, but they absolutely cannot afford to carry any extra weight around. So their digestive system is built for pure speed. They extract energy super fast and get rid of waste almost instantly. The number 1 rule of flight? No dead weight. Okay, a lightweight frame and a powerful engine, that's only half the story. You could have the most powerful car in the world, but without a great steering wheel and a smart driver, you're gonna crash. You need an advanced onboard guidance system. And for birds, that means super senses. Their eyesight is, to put it mildly, phenomenal. Just think about this. An eagle, soaring so high it looks like a speck to us, can spot a tiny rabbit on the ground from almost a mile away. That kind of vision is absolutely crucial for finding food, for navigating, and for avoiding danger when you're moving at high speed. And they've actually got 2 different visual setups depending on their job. You have birds like pigeons, who are prey animals. Their eyes are on the sides of their head. This gives them monocular vision, a huge panoramic, almost 360-degree view to watch for danger from any direction. But predators, like an owl or an eagle, have eyes on the front. This is binocular vision, like ours, and it gives them incredible depth perception for locking onto a target. All right, so we've got the frame, the engine, and the guidance system. But what about the actual surface of our flying machine? The wings, the body? This is where we get to what might be the true secret weapon of avian flight, the feather. You see, feathers are these multi-talented marvels. You've got the contour feathers on the outside that give the bird its sleek, streamlined, aerodynamic shape. Then you have the big flight feathers on the wings and tail that actually create the airfoil that generates lift. And underneath it all, you have soft, fluffy down feathers for insulation, keeping the bird warm. But the real genius is how they're built. A single feather is made up of all these little branches, and those branches have even tinier branches coming off them with little hooks. They're called barbules. And they literally zip together, like Velcro, to create a surface that's both strong and flexible. So when you see a bird preening, it's not just cleaning itself, it's literally zipping its feathers back into perfect shape for flight. So let's put it all together now. You take that ultralight skeleton, you add those massively powerful chest muscles, you fuel it with that supercharged respiratory system, guide it with those super senses, and you wrap the whole thing in this high-tech feathered surface. What do you get? You get a perfectly integrated system. You get a true master of the sky. But even with all that incredible built-in tech, flying is hard work. Takeoff is by far the most difficult part. It takes a huge burst of energy to overcome gravity and get airborne. And then there's landing, which is this incredible feat of control and timing, where a bird has to slow down just enough without stalling and falling out of the air. And they use all these amazing systems to master different styles of flight. You've got the non-stop, energetic flapping of a sparrow. That's powered flight. You've got the effortless gliding of an albatross over the ocean. You've got the soaring of a hawk riding invisible columns of warm air called thermals. And then you have the completely physics-defying hovering of a hummingbird. Each one is a specialist. So we've seen how pretty much every single part of a bird, from its bones to its breath, is perfectly optimized for getting airborne. Which kind of brings up a fun question to end on, doesn't it? After seeing their design, what parts of our own bodies, our heavy, solid bones, our tiny chest muscles, our inefficient lungs, make us so completely and totally unsuited for flight? Something to think about next time you see a bird fly by. Thanks for watching.